Good evening. In our next lecture series, we are going to discuss about the steady state errors. Now, in our previous lectures, we have discussed about the time domain specifications, and one of the parameter in your time domain specification was the steady state errors. So our discussion, I've just told that we will do it at the next lecture series. So today I'm doing my video on steady state errors. So what is the steady state error? Now, the deviation of the output of the control system from the desired response during the steady state operation is known as the steady state error. Now, it is represented as ESS. So, the deviation of the output of the control system from the desired response. Okay, so when the response, when it moves away from the desired response, then during the steady state operation, that error, now we call it as the steady state error, and mathematically it is represented as your ESS is equal to, it is limit t tends to infinity E of t. So this is in time domain, and when you just take the Laplace transform, when you apply the initial value theorem, now we get it is limit s tends to 0 E of s. And now the block diagram here, it clearly shows what is that error. So it is E of s is our error signal, which is nothing but the difference between the desired output and the reference input. So this error, we call it as the steady state error. So we are going to discuss this in detail in the following slides. Now we can see, now the closed loop response of any control system, it is given by C of s by R of s is equal to G of s divided by 1 plus G of s into H of s. Now since we have considered the unity feedback system, now we have written H of s is equal to 1. And from this, C of s is equal to, we just cross multiply R of s. So it is R of s into G of s divided by 1 plus G of s into H of s. Now E of s is nothing but, from the previous diagram, we can see E of s is nothing but, it is R of s minus, it is a unity feedback system. So the output is fed back to the input. So it is R of s minus C of s. Now therefore, E of s is equal to, it is R of s minus C of s. We are just going to substitute this. We solve that equation. Now we get it as R of s divided by 1 plus G of s. So our steady state error as per our definition is nothing but, you can see it is limit s tends to 0 into E of s. So it is limit s tends to 0 R of s, that is s into R of s divided by 1 plus R of s into, H of s into G of s. And H of s, since it is what you called as the unity feedback system, now we just write H of s is equal to 1. So therefore the equation for our steady state error, now it is limit s tends to 0 s into R of s divided by 1 plus G of s into H of s. Now how the steady state error, it varies based on the input R of s. Now you can see the equation, that is the error, it purely depends upon the input R of s. So now we define this ESS, that is a steady state error, in terms of certain constant which we call it as the steady state error constants. Okay, so initially we discuss about the static error constant. What are the static error constant and how it varies with respect to the input? So we are going to discuss that. Now you can see this following table, it shows the steady state error and the error constant, that is we call it as the static error constant. The steady state error is determined based on the static error constant for standard inputs like unit step, unit ramp and unit parabolic signal. So we have the input signals and a steady state error. Now how we got this? Now it is just a mathematical calculation. Now we know for, I'll just explain to you for the unit step input. So the step input, we know our R of s is equal to, for step input our R of s is equal to 1 by s for our step input. So it is 1 divided by s. So when you substitute this in our steady state error equation, so ESS, now it is equal to, it is limit s tends to 0, it is s into R of s. So s into R of s is 1 by s. So it is 1 by s. Now the whole thing divided by 1 plus, now the limit will substitute over here, limit s tends to 0 is limit s tends to 0 it is into G of S. Into G of S. So this S and this S, it gets cancelled. So the remaining thing, it is ESS is equal to, it is 1 divided by 1 plus. Now as per our definition for the static error constant, that is the first static error constant, we call it as positional error constant. So Kp is called as the positional error constant. So based on the definition, now it is limit s tends to 0 G of S. So limit s tends to 0 G of S is nothing but is Kp. So this is how we have got our steady state error for a unit step signal. It is 1 divided by 1 plus Kp, where Kp we call it as the positional error constant, and it is given by limit s tends to 0 into G of S. Similarly, now when the input is a unit ramp input, now the error constant we call it as the velocity error constant, and it is given by limit s tends to 0 S into G of S. Now when you substitute this again for a ramp input, now we know it is 1 divided by S squared. So when you substitute that, now we get our steady state error, it is 1 divided by Kv. Now Kv we call it as the velocity error constant. And similarly, now when the input is a unit parabolic input, so our constant static error constant we define in terms of Ka, which we call it as the acceleration error constant. Okay, so it is our steady state error, it is given by 1 divided by K. So Kp, Kv and Ka, now all three, they are called as the static error constant. They are called as the static error constant, which are used to define the steady state error for standard inputs like step input, ramp input and parabolic input. Now this static error constant method will not be applicable if the input R of S is other than the standard inputs. Okay, so if the input is other than the standard inputs, then the static error constant method is not applicable. Now where we move into the generalized error constant, now where the input can be any, that is R of S can be anything, need not be only the standard input, it can be of any type of input. So these are the static error constant with respect to your input unit step, unit ramp and parabolic signal. Now we know the steady state error for the various type of input. Now what happens if the type number of the system varies? What happens if the type number increases? Okay, so this tabulation, it clearly indicates now how this steady state error varies when the type number is increased. So suppose the steady state error, now the input is one, that is, it is a step input. Consider the input is a step input. Now we know the steady state error, the formula is 1 divided by 1 plus Kp. Now Kp is nothing but it is going to be a constant if the system is a type 0 system. Now we know the type number is nothing but the number of poles on the origin. Now that indicates the type number of the system. Now if the type number of the system, that is our transfer function G of S, now if it is going to be a type 0 system, now where for example it is like, say it is K divided by S plus A. Now this system, now you call it as a type 0 system, where you can see it is S power 0 is nothing but 1, which means there are no poles in the origin. So it is a type 0 system. For a type 0 system, now our Kp, that is a positional error constant, is going to be a constant for a type 0 system. So if Kp is constant, then now we have a constant error for a type 0 system. We are going to have a constant error. Now if the type number is increased, say we have increased the type number to 1, okay, which means there is one pole at the origin, then what happens is our static error constant Kp, now it is going to be infinity. It is going to be infinity. So when Kp is infinity, our steady state error is going to be 0. Similarly, for the next type 2 system, again Kp is equal to going to be infinity and our steady state error is going to be 0. So what we can conclude from this discussion is, if the input is a step input and if the type number is greater than 0, meaning if it is 1 or 2, then our error is almost, it is equal to 0. We don't have any steady state error for such a system. If it is a step input. Similarly, now if it is going to be a ramp input, now what happens is our steady state error, we know it is 1 divided by 1 divided by kV, where kV is the velocity error constant. Now for a type 0 system, now a kV is equal to 0, which means the error is going to be infinity. We are going to have infinite error for a type 0 system if the input is a ramp input. Now if the type number is increased, now we can see if it is type 1, then we are going to have a constant error for a ramp input, and if it is a type 2 system, then the error is going to be eradicated. So the error becomes 0. So as the type number is increased, the same thing can be discussed for a parabolic input. Now where we can see for type 0 and type 1 system, the steady state error is infinity. Whereas for type 2 system, now we have a constant error, and if the type number is increased to type 3 system, then what happens is our steady state error is going to be 0. So from these discussion, now what we can conclude is, if in order to eliminate the steady state error, the type number of the system has to be increased. And again, the type number, it cannot be increased just as such in order to eliminate the error, because now there comes the stability issues. So a balance has to be done between the type number, that is for a steady state error, and the stability of the system. So that's it regarding the steady state error for standard types of inputs, now which are defined using static error constant. So in our next lecture series, we will discuss what happens if the error is other than the standard input, that is the generalized error constants. Thank you.